All right, so the plan for today is just to talk about representing functions as power series, section, well, how does it say? 11.9. Um, and kind of a layout of the rest of the course is next week we have a wrap up of chapter 11, so Taylor and Maclaurin series and some applications, and then kind of just a brief review of chapter 11 on series, well, sequences in series, but most of it was on series. The week of 429 is Unit 3 exams, so very similar to Unit 1 and Unit 2 exams. There will be a sample exam posted next week. It'll be through Examity, same setup as before. You can use a formula sheet. So all of that, same idea as before. And then starting into chapter 12 for the last couple of lectures, we will do a little bit in chapter 12. Historically, chapter 12 has really been kind of Calc 3, but the engineering schools have wanted the math folks to put some of the vector calc stuff in Calc 3 instead of being a separate course. So that pushed a little bit of material from Calc 3 into Calc 2 and pushed a little bit of Calc 2 into Calc 1. We used to not cover as many integration techniques and so on in Calc 1. But so that's why we're covering something that seems like a little unrelated to a lot of what we did in Calc 2 and more related to Calc 3 because it is. So the introduction of the 3D coordinate system and some operations in that system, that'll be the last few class meetings. We have an optional review session from 1 to 3 p.m. on Wednesday the 8th. And then the final exam will be available, again, same kind of setup as the unit exams. It'll be available, taken on WebAssign through Examity from 5/3 that Friday through Friday the 10th. And just make sure to note that this is a Friday that's the due date. So our typical due dates have been Sunday, but just because of where the semester ends, the due date is on Friday. But I pushed it, the kind of start date up. Typically we would open things on Monday, but I pushed it forward to Friday the 3rd so that you still have one full week. You can have the weekend if you want to use that. And similar to before, like sample exam will be posted. You can use a formula sheet, taken on WebAssign using Examity. So similar setup to our previous exams. Okay, so that's kind of an overview of the last couple weeks of class. It usually seems like when we come back from spring break, like finals are right there, but because Easter was so early this week, our spring break was a little earlier, so we actually have a little bit more it's a little more of a relaxed time before we run into finals week. So it's a little nicer this year than it is some years. Our quote of the day today is 2 quotes. I think maybe with 2 different perspectives on, some overlap, and, maybe worth thinking of the differences as well. But one from Nietzsche, from his book Beyond Good and Evil, a German philosopher from, I guess, early 1900s. Whoever fights monsters should see to it that in the process he does not himself become a monster. And if you gaze long enough into an abyss, the abyss will gaze back into you. So this is one of his more famous quotes, the one about the abyss. And I think in some ways this quote is related to this quote from the Silmarillion, J.R.R. Tolkien's book. If you're familiar with like The Hobbit and Lord of the Rings, the Silmarillion is the book that gives kind of the backstory, kind of like the creation story of Middle Earth, the land that Hobbit and Lord of the Rings takes place in. But this quote from the Silmarillion: "For those who will defend authority against rebellion must not themselves rebel." So I think this parallels the monsters quote, but I think there are some similarities and some differences. So anyway, that's the quote of the day today, or 2 quotes of the day for today. All right, so moving on to representing functions as power series. So we can think of the series sum n equals 0 to infinity of x to the n when x is in the open interval -1 to 1. We know that this series has a sum. We know the series converges. and it converges to the sum 1 over 1 minus x. Usually we think of that in some sense kind of like in this direction. We have a series, we get its sum, and we can write out what the sum is. But of course, equality goes both directions. We could think of it this way as well. We could consider a function 1 over 1 minus x. It's just some function. We could have talked about it in algebra 2 or something and maybe looked at what its graph is, what its restricted values are, whatever. We have a function 1 over 1 minus x. We could, if we wanted to, choose to represent that function as a power series, sum n equals 0 to infinity x to the n. Now, there is an important note. If we just look at the function 1 over 1 minus x, its natural domain is all real numbers except 1. But if we look at the power series representation, its domain is just the open interval minus 1 to 1. It doesn't converge outside of that interval. So I really have to be cognizant of the interval of convergence of my power series representation. And I have to note that these two functions aren't like equal period end of story. They're kind of only equal on this specific interval open minus 1 to 1. If I go outside of there, if I was looking at x equals 2 or x equals negative 10, I could plug those values into 1 over 1 minus x with no problem, just looking at it separately. But I can't get convergence of this series in those cases. So these wouldn't be equal in those cases. That these functions or this power series representation of this function is only valid on the smaller domain, the intersection of the two domains. So let's look at a slightly more challenging example. Let's try to represent x squared over x plus 2 as a power series, and then maybe write out the first few terms, like a third or fourth partial sum, something like that. Well, I can leverage what I have up here. I can leverage the fact that 1 over 1 minus x looks like a geometric series on an interval of convergence. And I can ask, can I make this x squared over x plus 2 look like 1 over 1 minus x, or 1 over 1 minus something anyway? Well, I can pop off the x squared, and that gets me a 1 over. If I rewrite the denominator as 2 plus x, that gets me a little closer. Looking for something like 1 over 1 minus x, or maybe I would say 1 over 1 minus y, where y is some function of x. I could I could factor a 2 out of the denominator, divide the denominator by 2. And I'm getting pretty close now. I have 1 over 1 plus something. And if I just make this a 1 minus negative of that stuff, this is looking pretty good, right? This is going to be x squared over 2. 1 over 1 minus stuff is sum n equals 0 to infinity of stuff to the n. So this is what I have. And maybe I could write this as sum n equals 0 to infinity. So this negative x over 2 to the n is like negative 1 to the n, x to the n over 2 to the n. So that would be like negative 1 to the n, x to the n plus 2 over 2 to the n plus 1. So this would be a power series representation of this function, x squared over x plus 2. But I have to be careful here. I have to look at my interval of convergence. And I know I'm going to converge when and only when this ratio, x over 2, is between 0 and 1, or in absolute value. Or whenever absolute x less than 2. So that's the power series representation of my function, but only on this interval. Note that this kind of makes sense, right? This is centered at 0, and this thing blows up at -2. It has a restricted value of -2. I mean, I can't converge at -2, and I'm centered at 0. This, and I know my interval of convergence has to be symmetric from a theorem from last time. This is like the best that I could have hoped for, right? Is to converge on open -2 to +2. I mean, I suppose, I don't know, maybe I could have hoped that I would also converge at +2, but this is just about the best that I could have hoped for, is converging right up to that restricted value. And what are the first few terms? Well, for n equals 0, we have -1 to the 0. We have x squared over 2, and then minus x cubed over 2 to the second is 4, plus x to the fourth over 8, minus x to the sixth over 16, and so on. So we get our first few terms. We see it's an alternating series. At least I suppose for positive x, it's an alternating series. Okay. So we have a nice theorem here. If we have a power series with positive radius of convergence, then this power series is differentiable on its open interval of convergence. The derivative, we can differentiate our power series term by term. Remember, this isn't something that's a given. We could differentiate a partial sum term by term, yeah, no problem. But a power series, we know that as soon as we start taking a summation of infinitely many terms, we have to be very, very careful with what we do kind of inside the series. And we have a theorem now telling us that we can differentiate term by term under the summation sign or inside the series. And we can also integrate term by term. So we can integrate term by term here. We get x minus a to the n plus 1 over n plus 1 times cn. That's all under the series. And then plus, of course, a arbitrary constant of integration. So power series work very nicely on their open interval of convergence. We can differentiate them. The derivatives can be done term by term, and we can integrate them term by term as well. And then also the radii of convergence for both these new series, the derivative and the integral, are the same as the radius of convergence for the original series. Okay, so let's try to find a power series representation for arctan x. Now, arctan x doesn't look at all like a geometric series, so I'm not going to be able to make this arctan x look like 1 over 1 plus something or 1 over 1 minus something and get a geometric series type thing out of it. But one thing that I do note is that arctan x is kind of related to a rational expression, and that its derivative is a rational expression. The derivative of arctan x is 1 over 1 plus x squared. That does have that kind of form that's kind of like a geometric series, or that we can at least massage into a geometric series. Or in other words, f of x is the integral of 1 over 1 plus x squared dx. Or we could say that this is the integral 1 over 1 minus a negative x squared dx. And this looks like a geometric series. This is the integral sum n equals 0 to infinity of negative x squared to the n dx. We can see pretty clearly that this is going to be valid for x in minus 1 to 1. And now, again, if I want to integrate a series, really what this is saying is I can switch the order of the integral sign and the summation sign. That's really kind of what this is saying. And that's kind of what this is saying as well. That I can move the derivative from outside of the sum to inside of the sum. I can essentially swap the order of summation sign and integral sign, or summation sign and differential operator. In other words, I can make this sum n equals 0 to infinity of the integral negative x squared to the n dx. Or if we want to write that a little more nicely, that's negative 1 to the n, x to the 2n, like that. The negative 1 to the n, of course, just pops out of the integral sign. And the x to the 2n integrates to x to the 2n plus 1 over 2n plus 1. So I have this summation, and then I would get plus an arbitrary constant of integration. I want to, sorry, I had my notes turned to the wrong page over there. Okay, so I have this so far, but I pretty clearly see that f of x is actually arctan x, right? It's actually a specific function. So of course, I can't just have an arbitrary plus c here. It's got to match the original function. So what is c? Let's figure out that next. Well, I do note that f of 0 is arctan of 0, which is 0 in one hand. But on the other hand, f of 0, well, that's just evaluated at the center of the series. That's just the sum of a bunch of zeros plus c. So c has to be 0. Or I'll just erase my plus c here. And we see that on the interval x in minus 1 to 1, arctan x can be written this way. Or if we want to write out a few terms, this would be, so when n equals 0, we have negative 1 to the 0 is positive, so positive 1, x over 1, and then minus x cubed over 3, plus x to the 5th over 5, minus x to the 7th over 7, and so on. I guess I don't need the x over 1, but I put it that there so we could continue the pattern. So there's a power series representation for arctan x. X minus a third x cubed plus a fifth x to the 5th minus a 7th x to the 7th, and we can see the pattern. So what about something like this, writing x squared over a cubed minus x cubed as a power series? So again, I just want to massage this into looking like a geometric series. So this is going to be x squared times 1 over stuff. I want to factor out an a cubed. That'll give me 1 minus x over a all cubed. Or this is x squared over a cubed times sum n equals 0 to infinity of this stuff to the n, or x over a to the 3n. We know this converges if and only if the ratio is in open minus 1 to 1, or that turns out to be if x is in minus a to a. What about a function like this? This looks kind of qualitatively similar to this one up here. This was pretty straightforward to work with. What about this one, though? Right, 3 over x squared plus x minus 2 is a power series. Unfortunately, I don't see an easy way to make this look like a geometric series like I was able to for these examples. I have kind of like 3 fundamentally different terms here in the denominator. If I just had 2 different terms, I could maybe kind of massage it into a geometric series type form. But with 3 terms, it doesn't seem to work. But I might notice that I could factor this. This is going to be x plus 2, x minus 1. And I remember with partial fractions, if I can get fraction with x plus 2, or let's call it instead 2 plus x or 2 minus a negative x in the denominator, and another fraction with 1 minus x in the denominator, these will look like geometric series. So this is my strategy. I want to get to something like this. Can I use partial fractions to get there? Well, I know that my x's have to go away, so I've got to have probably opposite signs. If I do like 1 and 1 with a minus in between, this gives me a minus 1, minus 2, so it's got to be the other way. Right, this gives me a minus x plus 1, and then a plus x plus 2 in the denominator, or in the numerator. When I get a common denominator, my x's go away and I get plus 3. That is what I want. I can rewrite these a little better as something like minus 1/2 times 1 over 1 plus x over 2, and then minus 1 over 1 minus x. Or that's minus 1/2. This is going to be a minus a negative x over 2. So that's going to be 1/2 sum n equals 0 to infinity of negative x over 2 to the n. My lines are getting kind of smushed together here. Go. And then minus sum n equals 0 to infinity of x to the n. And I could maybe leave this here, but I could also kind of smush together my sums. If both of these series are convergent, then I can combine them under the same series. I had that theorem last time. So let me try to work towards that. So I have sum n equals 0 to infinity of what? It's going to be minus 1 to the n plus 1, x to the n over 2 to the n plus 1. I think I've got everything taken care of there. Yeah, looks good. And then let's do plus, just so I don't forget a minus sign later on. So now I have my indices of the series, sum n equals 0 to infinity, match in both cases. And my powers x to the n are the same in each of my series. I should be able to wrap these under the same series. And then factor out my x to the n. What do I get here? Negative 1 to the n plus 1 over 2 to the n plus 1 minus 1. Not the prettiest series coefficients in the world, but that's what I would get under a single power series. So where will this converge? Certainly not on the whole real line. We see that we have restricted values, so really no hope for that. This first one will converge when my ratio absolute x over 2 is less than 1, or when absolute x less than 2. And the second will converge when absolute x less than 1 is just kind of a straight geometric series. The more restrictive is that absolute x less than 1. So this is my interval convergence is open minus 1 to 1. This does make sense. This is a series centered at 0. I run into a problem at plus 1 and minus 2. So I don't really have any hope of converging outside of minus 1 to 1. Any questions so far? Okay, let's look at an integral approximation. Maybe trick, maybe technique, I don't know, depending on how you look at it. We talked about approximating integrals before in the course of back in chapter 7. But here's another approximation method. Let's try to approximate this integral to 2 decimal places of accuracy. Integral from 0 to 2/3 of 1 over 1 plus x cubed dx. And we could use Euler's method or something like that, but we could also use power series. So I note that 1 over 1 plus x cubed is 1 over 1 minus negative x cubed, or sum n equals 0 to infinity of negative x cubed to the n. Or this is sum n equals 0 to infinity of negative 1 to the n, x to the 3n. What's my interval of convergence here? Well, this x cubed, I don't have any divided by 2 or times 3 or anything like that. They're just going to have x in open minus 1 to 1. So what's the integral of 1 over 1 plus x cubed dx? That's the integral sum n equals 0 to infinity of minus 1 to the n, x to the 3n dx, like that. If I'm on my interval of convergence, open minus 1 to 1, I can swap the summation and the integral sign. When the integral sign comes in, the minus 1 to the n can come out. So now we have kind of this setup. Put a couple of parentheses and brackets in there to make things clear. And when I integrate x to the 3n, what do I get? X to the 3n plus 1 over 3n plus 1. Here, I'm not super worried about the constant because I just need an antiderivative because I'm looking to eventually evaluate this between 0 and 2/3 anyway. If we call this big F of x, we're looking for big F of 2/3 minus big F of 0. Well, note that 0 is the center of the series, so big F at 0 is just, well, maybe I should check just to be careful, but note when n equals 0, we have x to the first power, so we don't have a constant term in play here, so F of 0 is just 0. In other series, I could have a constant term that comes into play when I evaluate at the center, but here F of 0 is just 0. So I just have F of 2/3. Or this is going to be the series sum n equals 0 to infinity of what? Minus 1 to the n over 3n plus 1 times 2/3 to the power 3n plus 1. This like almost looks like it could be a geometric series, but that 3n plus 1 in the denominator really really doesn't let us figure out an exact sum for this. But we do note that we could write out a few terms. When n equals 0, I have what? Negative 1 to the 0 over 3 times 0 plus 1. That's just 1. 2/3 to the first power, so 2/3. When I increment n, that switches the sign. And then I have 1 over 4 times 2/3 to the fourth, and then plus 1 over 7 times 2/3 to the 7. Yeah, minus 1/10, 2/3 to the 10th. I noticed that I have an alternating series. I can use the alternating series estimation theorem. I know this converges. I know that the size of the terms decreases and so on. This 2/3 to a bigger and bigger power, along with this 1 over 3n plus 1, this is going to be decreasing, limiting to 0. Series converges. My alternating series estimation theorem says that my approximation or my error in my approximation is bounded in absolute value by the first term that I leave off. So let's bring up the calculator here. Let me switch my share over. So I have 2/3. That's about, what did I say I wanted? 2 decimal places of accuracy. Well, 2/3 is 0.67 or so. If I were to leave off the next term, it would be oops, had the wrong window open there, I guess, or wrong window selected. It would be 0.25 times 2/3 to the power 4. So that's 0.049. That would get me, I guess, 1 decimal place of accuracy. If I did 2/3 to the 7 divided by 7, 0.008, so that's getting close. I think I need one more. 2/3 to the 11 over 11, and that should do it. Or, whoops, sorry, 10. 10 over 10. So that should do it. So I can leave off the 1/10 times 2/3 of the 10th power because that's 0.002 or so. If I leave off that term, my error will be bounded by 0.002. That definitely gets me 2 decimal places of accuracy. So what's my estimate then? It's going to be 2/3. I'm just not having good luck with typing things into the calculator. So 2/3 minus 0.25 times 2/3 to the fourth plus 1/7 times 2/3 to the seventh Okay, did I type that all in right? So that looks right. And this gives me about 0.626 or so. And this should be accurate to at least 2 decimal places of accuracy. My error should be no more than 0.002. So with and in practice, my error might be much smaller, but this is an upper bound. So with just these first 3 terms, we can get at least 2 decimal places of accuracy. This component here that kind of feels like a geometric series really helps a lot. It really makes that error quite small quite quickly. If I didn't have this 2/3 to the 3n plus 1, if I just had like a -1 to the n over 3n plus 1, I'd have to add a whole bunch more terms in. That would go to, those terms would go to 0 in size much more slowly. But here that exponential decay helps a lot. So, a decent bit of work, and this is kind of an ad hoc method where I have to look at each function separately. If I had a different function that I wanted you to analyze the integral over, you'd have to look at that function separately, come up with its power series. We leaned heavily on the fact that this was an alternating series. If it wasn't an alternating series, we wouldn't have a good solid upper bound for it, for the error. So, several things kind of came together nicely here. We'll actually see when we talk about Taylor series, we'll be able to apply something like this kind of technique a bit more generally. So we won't have to kind of get lucky in a sense and end up with an alternating series. And we'll have kind of a more formulaic approach to get a power series representation. That's one of the big benefits of Taylor series, is these kinds of approaches that from our perspective right now have to be very ad hoc, very problem dependent. You can kind of wrap them all under a similar umbrella with Taylor series. So that'll be the next couple sections that we see. Oh, and then one last question. What if instead of integral 0 to 2/3, what if it was integral 0 to 2 of 1 over 1 plus x cubed dx? There's no problem with that integral. Integral 0 to 2, 1 over 1 plus x cubed dx, that is a perfectly fine integral to try to do. It's not like we're trying to integrate from 0 to -2 or something. So, I mean, that integral will exist. We should be able to approximate its value. But could we do it this way? Could I just come down here and put a 2 in here and do the same analysis like I did here? Well, the answer is no. I mean, on one hand, we see that the 2 and 2 to the fourth and 2 to the seventh, those are going to overwhelm this denominator, and our terms aren't even going to go to 0. But really, this power series representation is only valid on open -1 to +1. So we were really relying on the fact that the region of integration lay in this interval of convergence. If we were trying to integrate over 0 to 2, we're no longer in this interval of convergence. That's not going to work. Interval of convergence. I think I said integral of convergence. Okay, so next example, Let's try to solve a differential equation using power series. So for complicated equations, this is something that would be covered in a differential equations course, but I think this is one that's approachable enough that we can cover it here. And we kind of saw before, I guess I don't need the calculator anymore. I'll switch back to OneNote, so it's a little bigger in your screen. We kind of saw before that one of our methods of solving differential equations was kind of guess and check. We guess a certain form, and then we do some algebra and figure out what do the details have to be, right? We might guess y equals e to the RT, and then do some algebra and figure out what does r have to be. Well, can we search a bigger function space? Can I say let y equal sum n equals 0 to infinity of Cn x to the n, and I'm going to try to figure out what my Cn's have to be, what C0, C1, C2, etc. has to be. Well, I need y prime equals y. That's my criterion. So let's suppose that we're on the interval of convergence. Then y prime is sum n equals 0 to infinity of n Cn x to the n minus 1. I might notice in y prime that my n equals 0 term is just 0 C0 x to the, well, I guess x to the minus 1. That's a little funky, but because I have n equals 0, this n equal, because I have n here equaling 0, when the index n equals 0, this index n equals 0 term is just 0. So really I could just write this as sum n equals 1 to infinity of n Cn x to the n minus 1. Now I want to equate these two series. There's a couple ways I could do this. I guess I could do like y prime minus y equals 0, or I could just put them on two sides of an equal sign and see what happens. So if y prime equals y, that means that sum n equals 1 to infinity of n Cn x to the n minus 1 should equal sum n equals 0 to infinity of Cn x to the n. If I put these on two sides of the equal sign, I see that my summation indices and my powers of x don't quite line up nicely. So what I'm going to prefer to do is to put them on the same side. And what this will let me do is just work with my summation indices and my powers of x and try to get everything to where I can, in a sense, like factor out the summation symbol and factor out the x to the n, similar to how we did up here. Okay, so sum n equals 1 to infinity. What does the n equals 1 term look like? It looks like 1 C1 x to the 0. I could re-index this as sum n equals 0 to infinity, or we could have used a different variable. This is essentially just a change of variables. So my first term here looks like 1 C1 x to the 0. My first term down here should look like 1 C1 x to the 0, or it should look like n plus 1 C subscript n plus 1 x to the n. That's a good way to get your series lined up correctly with the indices when you do a change of index like this or a change of variable, is just to say, what's my first term when I started? And then whenever I go to my new indexing, make sure that first term looks the same. And here it does, so we're happy with that. And then we have minus sum n equals 0 to infinity, Cn x to the n equals 0. Now my summation indices are the same. I can wrap this under a single sum. Why can I do this? Well, because that I mentioned before that we're assuming that we're working on the interval of convergence of the original series and let's say the open interval of convergence of the original series, and the derivative has the same open interval of convergence by the theorem up above. So these two series converge, and I can wrap them under a single summation, wrap their difference under a single sum. But now what do I see? I see that I have a power series, the sum of a whole bunch of coefficients times x to the n equaling 0. Unless this is a super goofy power series that like only converges when x equals 0, and that's the only domain we're talking about. Well, but then the derivative wouldn't exist, so that wouldn't make a whole lot of sense, right? The only way that we can have this whole series being 0 is if each of these terms are 0. So I have to have, oh, is there a question? Okay. So I have to have n plus 1, cn plus 1 minus cn equals 0 for n bigger than or equal to 0. Or in other words, I have to have cn plus 1 equals cn over, don't need a parentheses there, cn over n plus 1 for n bigger than or equal to 0. So if I know what C0 is, I can find C1. If I know what C1 is, I can find C2 and so on. So what's C0? Well, I know that I have one more constraint that I haven't used. That's my initial condition, y of 0 equals 1. But y of 0 is just some n equals 0 to infinity of Cn times x to the n, or 0 to the n. Or, well, that's just C0. All of the terms from the n equals 1 term on have a power of x in them, and that zeroes out. So we have that C0 has to be 1. So we combine these, C0 is 1. C1 is what? C0 over 1, or 1. C2 is C1 over 2, or 1/2. C3 is C2 over 3, or 1 over 2 times 3. C4 is C3 over 4, 1 over 2 times 3 times 4. And I think we see the pattern. Cn is 1 over n factorial. So what's my solution to the initial value problem? That what's my function that solves this differential equation subject to that initial value? Well, my solution is sum n equals 0 to infinity of, well, 1 over n factorial times x to the n, or x to the n over n factorial. We can do a ratio test on this and see that it converges on the whole real line. This n factorial on the bottom really drives all the terms to 0 very quickly, regardless of how big x is. The n factorial grows like n to the n, so it's always going to overwhelm the x to the n on top. And something interesting we might notice is you might have looked at this differential equation and said it's kind of silly to solve this with a series because we know what the solution is, right? Y prime equals y is an easy differential equation to solve. A function that's its own derivative is just an exponential function, and y of 0 equals 1 constrains it to be e to the x. We've actually discovered another power series relationship, that e to the x equals sum n equals 0 to infinity x to the n over n factorial, actually on the whole real line. So that's kind of nice. We don't have just some small interval of convergence like we did with the geometric series, but we have a really nice power series representation of e to the x on the whole real line. So we answered the question, I guess, at this point. But then these bits were things we got for free. It's really the reason we're doing this question. Kind of an interesting thing you could look into if you want to. Well, what if we looked at, say, y double prime equals negative y? Well, we know that solutions to that look like sines and cosines. Can I come up with some initial conditions, do a similar process to this, and get some kind of power series representation for sine x and cos x? Might be something interesting that you can look at and try to work through it, see if you can come up with an answer, and then you can look up Maclaurin series for sine x or cos x. You could Google that or look it up in the book and see if the series you came up with matches the series that is like published everywhere. So but through differential equations, we've matched up e to the x, and of course we're leaning heavily on the uniqueness of the solution here, that these have to be the same function because differential equations under some criteria have unique solutions. So this is a differential equation with a unique solution, so these have to be the same function. We've derived a power series representation for e to the x on the whole real line. All right. I think we could do one of these two. Let's just go through this one. Find a power series representation for this function log of 1 plus x over 1 minus x. And here, I suppose we could try to do something directly with the log, but that seems like it's going to be pretty messy, right? Log of 1 plus x over 1 minus x, that doesn't seem like a function that I really want to deal with. But I could rewrite it. Using a property of logs, the log of the quotient is the difference of the logs. And then I could actually note that f prime of x, 1 over 1 plus x, minus 1 over 1 minus x, but the chain rule pops out a minus, so that's a plus. The derivative actually works pretty nicely. This just looks like some geometric series. This is 1 over 1 minus a negative x, or this is going to be sum n equals 0 to infinity of negative x to the n plus sum n equals 0 to infinity of x to the n. Or I can see that this is going to be sum n equals 0 to infinity of minus 1 to the n plus 1 x to the n. And I can see that my coefficient for n even is just plus 1, and for n odd is minus 1 plus 1 is 0. So all of my odd powers go away, and I'm just left with even powers. So sum n equals 0 to infinity. I only want the even powers. And Oh, did I say +1? It's +2. Right. -1 to even power is +1, and then +1 is +2. So I want 2 times, and how do I make an even power? That would be x to the 2n. So up here I'd have even powers, like when n equals 0, I'd have x to the 0. I'd have a 2x to the 0. The n equals 1 term, the coefficient zeroes out, so that goes away. The n equals 2 term, the coefficient is 2, and I get x squared, and so on. Rewriting it this way, when n equals 0, I get 2 x to the 0, just 2. When n equals 1, I get 2x to the second power. When n equals 2, I get 2x to the fourth power, and so on. So I've just kind of re-indexed here a bit. And now importantly, this is f prime of x, which is equal to this. This is, of course, on -1 to 1. We can't log a negative or divide by 0, so that that constraint is clear from the beginning in this case. And then what do we do now? We just integrate. And again, we can, as long as we're on our interval, our open interval of convergence, we can swap the summation and the integral sign. So I think I've got all of my parentheses right there. Yeah, looks good. And then my integral is going to be x to the 2n plus 1 over 2n plus 1 plus c. And I can evaluate f at 0. So on one hand, I notice that all of the terms in my sum, in my series, are going to have at least 1 power of x. From integrating, I picked up a power of x. So the n equals 0 term has an x to the first. So when I plug in 0, this series zeroes out. So on one hand, f of 0 is c. And on the other hand, it's log of 1 plus 0 over 1 minus 0. Or log of 1 over 1 is 0. So c is just 0. Or I have that f of x is f of x is just that series on the open interval in -1 to 1. And when we come back, we'll wrap up with one last problem, computing the integral of e to the x squared dx as a power series. We know we can't write this, write an antiderivative for this in terms of nice functions, but can we write it in an infinite series? We'll take a look at that next time.